Okay, let's begin then. So I'll start with a recap of what we did last time, right? So last time we solved the positive and the negative eigenvalue problems of the Laplacian, okay, which were the screened Poisson equations and the Helmholtz equation respectively. We solved those two, but we only found the spherically symmetric solutions, right? So this time what I want to do is to get rid of that spherical symmetry assumption and get all the solutions, right? So what did we do? We found spherically symmetric solutions of the screened Poisson and Helmholtz equations respectively. Right, which are just grad squared f equal to kappa squared f and grad squared f equal to minus kappa squared f, kappa belonging to the real numbers, right? Right, which are the positive and negative eigenvalue problems. So we solved them and we for the spherically symmetric solutions, and we found that the spherically symmetric solutions can be written down in a very simple form in all number of dimensions, right? We took the d equal to 1 case, we found that the spherically symmetric solution was either cos x or cos x depending on whether you're doing positive eigenvalue problem or negative eigenvalue problem. And we noted a very important feature of these two solutions, that they are spherical averages. And then from there we generalized that notion to higher dimensions and just wrote down a solution which gave us all the higher order Bessel, all the zeroth order Bessel functions I and j, right? Bessel functions as well as spherical Bessel functions, that depends on dimension, right? D equal to 2 it gives you the cylindrical Bessel or Bessel functions, and in d equal to 3 it gives you the spherical Bessel function, right? So we found that I naught of d comma kappa r is equal to spherical average of e to the q dot r, where q is ranged in a kappa radius kappa d minus 1 dimensional sphere, right? So q is some k times n hat, where n hat belongs to the d minus 1 dimensional sphere, and j naught d comma kappa r is e to the I q dot r, again q equal to kappa n hat, such that kappa n hat belongs to st minus 1. Right? And we define this d minus 1 dimensional sphere. This is, I'm sure everybody knows this, but nevertheless for completeness let me write down, it's the set of all points belonging to Rd such that it satisfies the sphere condition. Right? That's the unit sphere in our dimensions. In d equal to 2 you can see that that gives you the circle, which is x squared plus y squared equal to 1. And d equal to 3 it gives you the sphere and so on, right? And one more thing is that, so just for completeness let me write down that I naught of d equal to 2 kappa r is what people usually call capital I naught of kappa r. Let me use rho for 2 dimensions. Similarly j naught of d equal to 2 kappa rho is what people usually call j naught of kappa rho, and I naught d equal to 3 kappa r is usually called I naught, little I naught of kappa r, and j naught d equal to 3 kappa r is usually called little j naught of kappa r. Okay, and these are called the spherical Bessel functions. Of zeroth order, right? So that's where we stopped last time, Okay, so these are all the spherically symmetric solutions because they only depend on the radial coordinate r or rho, depending on the notation. Now we want to get rid of the spherical symmetry assumption and get the higher order Bessel functions, right? When you get rid of the spherical symmetry, you do so systematically, and you get this tower of Bessel functions, IL and JL, right? Be it spherical or cylindrical or whatever. Okay, so let's do that now. And one more thing, remember, I promised you last time that we will do this by taking this 0th order solution and differentiating it, right? And that's what we want to see today. And from there, you will get everything about Bessel functions, recursion relations, Jacobi-Unger expansions, Rayleigh-Taylor expansion, not Rayleigh-Taylor, Rayleigh, I think, yeah, Rayleigh expansion, and so on, right? So let's do that. So I will do it for positive eigenvalue problems only. I mean, at first, negative eigenvalue problem is just an analytic continuation. I will write down the results, okay, and I'll also show you why those are correct. Okay. So let's focus on the positive eigenvalue problem now. Let's consider grad squared f equal to kappa squared f. Okay. First thing to notice is that grad squared is just del x squared, del y squared, plus del y squared, plus del z squared, say in the 3 dimensions. Now that operator commutes with del x, right? Because del x acting on grad squared on f is the same as grad squared acting on del x on f. Because del x goes through all these partial derivatives, it commutes, right? So this would imply that del xi, where I labels x or y or z, or if you're in higher dimensions or lower dimensions, it just labels the coordinates, Cartesian coordinates. These are Cartesian, remember, xi are the Cartesian coordinates. Label Cartesian coordinates. Del xi on grad squared of f equal to kappa squared remember is a constant, del xi on f, which implies, since these two commute, grad squared on del xi on f equal to kappa squared on del xi on f. Okay? So that means we have found another solution. If you give me sine, or let's say you're given the d equal to 3 j0 functions, this j0, which is what? Sine kappa r by kappa r. I derived it for you last time, right? j0 is just sinc. Sine kappa r by kappa r. If you want to get another solution, it's not spherically symmetric, differentiate with respect to x, or differentiate with respect to y, or differentiate with respect to z. You get 3 different solutions, right? That's what this means. Because I've shown you, starting from here, that this is also a solution. Therefore, del xi acting on f is also a solution. Okay? Okay? Now this solution is not spherically symmetric, notice, right? Because del xi, say you take x for simplicity, 2 dimensions. This is not spherically symmetric. Right? For example, let's consider d equal to 2 and let's consider del x, say, of some function, some solution. It can be I0, J0, or it can even be green functions that we will discuss later on. Okay. So for now, just concentrate on I0 or J0. It can be either I0 or J0. Now del x of this is what? It's just del r of f of r, which is just df over dr, times del r over del x, but del r over del x is just x by r. So this gives you x by r. And x is just r cos theta. Actually, maybe I should use rho because we are in d equal to 2. Rho. X is just rho cos theta. So this is equal to cos theta df over d rho. So it does not have spherical symmetry anymore. It depends on the theta variable, right? So once you differentiate with respect to Cartesian coordinates, of course you get spherically non-symmetric things. You differentiate once, you get the level 1. I will call the number. Okay, let me come to that. Okay, so this is not spherically symmetric, that's clear. This, oh, that's because r squared is summation I xi squared, which means r dr or del r del xi is just 2xi, right? So then the twos cancel and you get what you want, del r del x equal to x over r, right? Okay. Now notice that one derivative is not special. You can have however many derivatives you want. You can do del x, you can do another del x, or you can do del x and another del y, or you can do del x, del y, del z, del x again, and like you can do however many derivatives you want. Okay. So the number of derivatives you do, I will call the level of the solution. So at level 1, you have del x of f, del y of f, del z of f, or if you are in arbitrary coordinates, you just have del xi of f. Okay. At level 2 though, you have many different things, right? So let's say we do two derivatives. Let's say we do grad squared on del xi, del xj on f equal to kappa squared del xi, del xj on f. Okay. Now I can do this in many different fashions, right? I can do del x squared, I can do del y squared, I can do del x squared minus del y squared, right? There are many different options. Example, 2D, I have many different options. I can do del x squared, I can do even 3 del x squared, or I can do del y squared, del x squared minus del y squared, del xy, and so on. Many different options. I can do 3 times this or 2 times that, and so on. Which basically means I can put numbers there dependent on ij, right? So this basically means y11, which is some number, times del x squared, plus y12 del x del y, plus y21 del x del y again, plus y22 del y squared. Okay, so y12 there as well. Ij, sorry, ij, right? But in just what I said, you already noticed that y has to be symmetric, right? Because you do y11 del x squared plus y12 del x del y plus y21 del x del y. That's just y12 plus y21 del x del y. Okay, right? Which you can just choose to be just y12, 2y12. It doesn't matter, right? Because even if it was not symmetric, say y12 and y21 differed, it's only the sum that will matter in this product. Okay, y12 plus y21. So it doesn't matter. You can just choose it to be symmetric. Okay. So the first lesson we learn is that yij has to be symmetric. Okay. That's one thing. But another thing is that if yij say was just delta ij, identity tensor, then yij times del x del xi times del xj is just delta ij del xi del xj, which is just del xi delta ij del xj. I'm using the convention, summation convention implicitly, the Einstein summation convention, so everything is summed over. Whenever two indices are repeated, up and down they're summed over. So this is summed over. So this is just what? If you want me to write the summation explicitly, this is just 1 to d or 1 to 2, which I can just write explicitly, which is just del x squared plus del y squared, but that's just the Laplacian. Right? So you notice that this differential operator acting on f will just be Laplacian acting on f. Therefore, Yij del xi del xj acting on f would be grad squared acting on f. But since f is a spherically symmetric solution of a spherically symmetric positive eigenvalue eigenfunction, this is just kappa squared f. So it hasn't generated for you a new solution. Okay, like in this case where if I differentiated with respect to x, you got a new solution. Here I am not getting a new solution. I am getting f back. So basically, what that is saying is that this is not a new solution anymore. So you have to get rid of Yij equal to delta ij. Okay, that basically says y has to be traceless. Okay, because what is the trace of a matrix? If you take a matrix A and write it as some number times identity plus something else, which does not have an identity piece. Okay, that number, which is the coefficient of the identity, is the trace. With some number proportional to the trace, right? So when you say it does not have delta ij, it just basically means it's traceless. Okay, Yij has to be traceless. So it has to be a symmetric, traceless or trace-free tensor. It has to be an STF tensor, where STF stands for symmetric, trace-free. Okay. Yeah, now we can see. Good. So we are done with two derivatives. Okay. So what we have learnt at the level of two derivatives, level equal to 2, is that you have to basically take Yij del xi del xj, but Yij has to be symmetric trace-free. Patience. We'll get to the ILs and JLs soon. Okay. But this is all simple algebra, right? We're doing very simple things, but you'll eventually see that all these simple things just give you IL and JL very quickly. Okay, now let's do level equal to 3. Let's do 3 derivatives. So this was 2 derivatives. Can you see this? Not quite. Yeah, this was 2 derivatives, aka level 2. Let's now do level 3. Okay, which means grad squared acting on some yi1, yi2, i3. Instead of using ijk at level 4, you'll run out of numbers, run out of letters. So let's just use i1, i2, i3, i4, so on. Okay, del xi, which I will just call i1 because notation otherwise will get very cumbersome. F equal to yi1 kappa squared, sorry, acting on yi1, i2, del i1, del i2, del i3 on f. Cool. Okay. Let me just put a 3 factorial. Doesn't matter, right? I'm just pulling things out of y just for fun. Okay, you'll eventually see why. I mean, it doesn't at all matter. Just consider it as, yeah. I mean, just forget about it. If you don't want it, forget about it. If you want it, put it there. I'm just putting that 3 factorial because it's a symmetric trace-free tensor. Here also will be a symmetric trace-free tensor. So just normalization. So now notice that if for example, okay, first of all, y has to be symmetric. Same argument holds, right? Because del del i1, del del i2, del del i3 is a symmetric tensor in i1, i2, i3. So this has to be symmetric. So first lesson we learn again is that Yij has to be symmetric. So immediately we also learn, since we have enough experience to say that in all dimensions yij, y should be symmetric, yi1, i2, i3, so on should be symmetric. Sorry, not all dimensions, all levels. This means yi1, i2, i3 has to be symmetric. I mean, is chosen to be symmetric. Okay. Secondly, notice that, say for example, let's take yi1, i2, i3 equal to delta i1, i2. Okay. M, say some other matrix. Let's say M let's call it, I don't know, what should I call it? Say I4, I2, I3. No, that's not good. That's not good. What's a better way to write this? Give me a moment. Yeah. So okay. Let's take a particular example. Let's just say this is some number. Let's call it n I3. That depends on I3. Okay. So say y111 is n1, which is some number, say 1 or 2, times an identity tensor in 1 and 2. Okay. Okay. This sounds good. But if you take this, you see why I'm taking this, right? Because if you run this argument now, yi1, i2, i3, del i1, del i2, del i3 will just be ni3, delta i1, i2, del i1, del i2, that's just del squared, del i3, which is just ni3, del i3, del squared. Okay. But then now let's act yi1, i2, i3, del i1, del i2, del i3 on f. This will just be ni3 del i3 grad squared on f, but grad squared is just kappa squared on f because f is positive eigenvalue spherically symmetric solution. And what you have found is that I thought we were doing a level 3 solution, but at level 3, if this had some delta i1, i2, we have found a level 1 solution. Because this is just level 1, right? These two are just numbers. So this is just level 1. We've gone back to level 1. Okay. And we already have all the level 1 solutions. We don't want to reproduce that at level 3. Okay. Which basically means it can't have a piece like this, delta I1, I2. Same thing will happen if it had a delta I2, I3 or an I1, I3, right? Which basically means it has to be, again, what we find is that y has to be trace free. If you take any two indices the same, okay, and find the trace, there shouldn't be a trace. Okay. So what this means is that we should again take yi1, i2, i3 has to be STF. Right? Make sense? To get different solutions so what we are trying to do is to do one derivative and then do two derivatives and then do three derivatives and so on and so forth, and at every level I want different solutions. At level 1 I got a set of solutions, at level 2 I get another set of solutions, at level 3 and I get another set of solutions. I don't want the solutions here to be the same as the solutions above. okay, which is why I'm doing this. Okay. With these many constraints, I see that at every level you get different solutions, right? If you don't want to call it STF, just remember this fact. Okay. If you said two of the indices equal, I mean, if in two of the indices, if it's an identity tensor, then it shouldn't work. Okay. That makes sense? Okay, great. Now, for now, by now we have enough experience, right? We know enough experience to say at level L, where you have L number of derivatives, basically it means that it should be symmetric. It should be a symmetric trace-free tensor, the y outside, right? Therefore, at level L, we get the solution for solutions y I1, I2, all the way up till IL. I will normalize it by a L factorial. If you don't want it, don't keep it. Del I1, del I2, so on up till del IL. Where this is a symmetric trace-free tensor, or an STF tensor. Now, for those of you who have done spherical harmonics and Legendre polynomials and so on from a symmetric trace-free tensor point of view, you're probably already screaming, saying, oh, how did a symmetric trace-free tensor or a symmetric trace-free polynomial come up by solving Bessel functions? Right? Because I thought those were zero eigenvalue things, those were spherical harmonic things. As we'll see, these are very closely linked. Okay. Anyway, so we have found all the solutions, right? Now all we need to do is to take the I naught, okay, and differentiate it, where the y is some arbitrary thing. Okay, so let's start differentiating. Now, still you might be very uneasy and you might say, oh, y is still arbitrary. I can choose y to be anything I want as long as it's symmetric trace free. That doesn't fix y to be something, right? Right? That's not true. Okay, as we'll see. So let's start differentiating. Okay. So let's start differentiating. Okay. So f of r is some spherically symmetric solution. F of r is just function of r. So let's say I do del xi of f of r. That's just this. Level 1 is just this. If I do, oh, by the way, so f of r is just equal to df over dr times xi over r. Okay, this I showed you some time ago, right? Right there. If you do two derivatives, what happens? Say I1 del x I2 on f. So the first time it gives you this del x I1 on 1 over r df over dr, right? 1 over r df over dr should remind some of you of Bessel recursion relations. Anyway, let's forge ahead. Let's not make hasty conclusions. Xij I2, right? You have to do this once again. So let's do that once again. That gives you d over dr of 1 over r df over dr, right, times xi1 xi2 over r. Let me put that r over here, plus 1 over r df over dr times del x1 of this, which will just give you I1 I2. Right. Okay. So what we have found is that del x I1 del x I2 on F is equal to 1 over R d over dr acting twice, 1 over R ddr, 1 over ddr acting twice on F times xi1 xi2 plus 1 over R df over dr times delta I1 I2. Okay. Okay. Now when you hit this with a y, since delta I1 I2, so if say you had I1 I2 I3 and then you had a delta I1 I2, this is just taking a trace. Okay. And yij's are symmetric trace free, so this term won't contribute. Okay, which is good news. But let's forge ahead. Let's do level 3. Let's do another derivative. So let me write what I just said. I1 I2 del x I1 del x I2 will just be y I1 I2 x I1 x I2 STF polynomial, okay, times 1 over R ddr squared acting on F. Okay, good. Let's do another derivative. Say I1 I2 I3. Let me put it this way. I3 I1 I2, because I1 I2 we already know. This is just del x I3 acting on 1 over R ddr squared acting on F I1 I2 plus 1 over R ddr acting on F delta I1 I2. Okay. Which is just, so this, let's hit it on this first term. This, when it hits on this, will give you again a ddr, okay, acting on this full thing, and then del R del x, which will just give you an xi3 by R. So that will just be a 1 by R ddr cubed acting on F xi1 xi2 xi3, and then this will come and hit this, which will give you two delta functions, right, plus 1 over R ddr squared acting on F times delta I1 I3 x12 xi2 plus delta I1 I2 xi3. Then this will come and hit this term, which will give you 1 over R ddr squared. So let me absorb that term here. It will give you, guess I'm doing this correctly, delta I1 I2 xi3 again, plus when this hits that, that'll just give you 0. So that's it. Okay. So again, when y hits this full term will go away, because each of these pieces is a delta. That's like taking a trace, and we have already shown that y has to be trace free. Okay. Okay, which implies that y I1 I2 I3 del x1 del x y1 del x I2 del x I3 acting on F should be equal to y I1 I2 I3 xi1 xi2 xi3, which are these, times 1 over R ddr to the 3 acting on F. And in general, you can keep doing this, you can show it by induction if you want, but it's clear that in general y I1 I2 all the way up till IL del x I1 del x I2 all the way up till IL acting on some function which is just a function of the radial coordinate is equal to y I1, I2 all the way up till IL into polynomials I1 okay, my notation is not that good. These upper indices are also summed over, by the way, sorry. Okay, I'll fix this in my notes. X so on up till xil acting on 1 over r ddr to the L on F. Okay. Now that is the solution, okay, where you have broken the spherical symmetry level by level, right? I said that we will break the spherical symmetry systematically, and that's what we have done. We have taken one derivative, we have broken the spherical symmetry, but systematically at level equal to 1. Then 2 derivatives, level 2, 3 derivatives, level 3, and so on and so forth. So at Lth derivative, this is the solution of the Laplace of this eigenfunction equation. Okay. 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 So what we find, oh sorry. Okay. What we find is that to solve grad squared f equal to kappa squared f, spherically symmetric solution was easy to write down. Yeah, which is just spherical average. To get the less spherically symmetric solutions, the Lth level solution, all you need to do is to differentiate that with respect to r by this kind of derivative and then multiply by such a thing. The only thing left to do is determine what this such a thing is. Okay, some of you I see smiling, right? Because those are just the spherical harmonics. Okay, we'll come to that in a moment, but let me move the board all the way to the beginning. Okay, so we come back here, and what we have just seen is that, shall I, yeah. Therefore, we learn that y I1, I2 all the way up till IL, x I1, I2 all the way up till IL times 1 over r ddr to the L f. Okay, let me normalize it by a 1 over L factorial is a solution of grad squared f equal to kappa squared f. Okay. Now the radial part of the solution is what one calls the Lth Bessel function. Okay. So this bit. So therefore, IL of d kappa r is defined. So radial part but these all, remember, has a radius in them, because if it was just x, y, z, x is r times angular dependence, y is r times angular dependence, z is r times angular dependence. So let me say xi1 is r, xi is r times ni. Okay, by which I mean if it was x in 2D, okay, x is just r cos theta or rho cos theta. So I want to take the rho out, and ni will have that cos theta. Okay, so if I have, let me write n, all these as n. I just want to show you what people usually call the Bessel function, right? So IL is just r to the L 1 over r ddr to the L acting on I naught. And I naught we know, right? Spherical average, can write it down in any number of dimensions. In particular, cylindrical and spherical Bessel functions you can write down, and then you need to differentiate. Since this is the definition, the recursion relations of the Bessel functions are obvious. And if you want the Frobenius series expansion of the Bessel function, put the I naught take the I naught spherical average definition, series expand the exponential within the average, find the integral, put that in there, you get the spherical, you get the Frobenius for IL. Similarly, JL. So in JL, people usually put an I to the L here. Okay, that's again just a normalization. D kappa R is R to the L 1 over R ddr. Actually, we should put a kappa to the L here because we have to differentiate with respect to the argument here, right? Because the argument is kappa, we have to put a kappa to the L, which you can check. So then it becomes obvious why there is an I to the L, right? Because we're doing an analytic continuation of this. A of L J naught T comma kappa R. So these are the higher order Bessel functions. Okay. Now this is nice. We have a working definition, we can just write everything down, but it's a bit unsatisfactory, right? Because the spherically symmetric solution was so simple. You could just write it down in one line and you can write it down in any number of dimensions with just one step, right? Take the spherical average, just write down the integral. It will be an integral representation. In some dimensions you'll be able to do it, in some dimensions not. Okay? But you have an answer with which you can do asymptotics, you can do series expansions, you can do all kinds of things. But here it's a bit unsatisfactory, right? Because you have to take the spherically symmetric solution, which is some spherical average, put it in here, take lots of derivatives. These derivatives are not trivial, right? Because you have to do R times 1 over ddr of 1 over ddr is just not 1 over R squared ddr squared, right? It's not that trivial. Yeah. So you have to do some work. And that's quite a bit of work. And we want to be a bit lazy, right? Because while we are solving electromagnetism problems, we don't want to come back and do all these derivatives. I just want to write an answer down, series expand, and see the physics rather than get stuck in this algebra, right? So let me show you a much nicer way of writing these higher Bessel functions down, okay? And that nice way is again a spherical average. Here we wrote down this spherically symmetric solution as a spherical average. I want the non-spherically symmetric solutions also as a spherical average. What we'll see is that spherical average has to be a modulated spherical average. We'll see what that modulation means. Just a minute. Okay, but this much I guess is clear, right? Okay, let's get rid of those things. Okay. Okay, great. So what have we found? We have found the solution. So remember that the solution was just some y times this. So y is some st of tensor times this ni1, ni2 and so on and so forth till nil times x r to the l 1 by r ddr to the f. So let's take this r to the l inside once again and let me just write this down. Okay, I'm just curious about this. I just want to know what this is. Okay. Because remember at level L, anyway, let me just do this. Y I1, I2 all the way up till IL. Okay. Anyway, sorry. That's not the right starting point. Let me start here. At level L, this is what one needs to do. I'm not keeping track of this 1 by L factorial because that's not really necessary here. It's just a normalization. But I'll keep track of it in my notes. Over IL, right, acting on some f of r is the Lth level solution. Okay, and we just did all these differentiations properly, and we found the radial part was just the Bessel functions. We defined them. No? But this FFR, notice, was just some spherical average. Let me do I naught. Then this is just spherical average e to the q dot r, such that q was just some kappa n hat, and n hat belongs to st minus 1. Okay. These derivatives will go through the spherical average, because the spherical average is over a is over a sphere, but that's in q. Okay, doesn't matter to the r, so this will go through. So this will be y I1, I2, all the way up till IL. All these derivatives, when acting on q, what will it give? This is just e to the q I1, sorry, q1 r1 plus q2 r2 plus q3 r3 all the way till q drd. So when del x I1 acts on that, it'll just give you q1 down, right? So this gives you q1, q I1 down, and then q I2 all the way up till q IL times e to the q dot r, q equal to kappa n hat belongs to st minus 1. Okay, and this is just a number. I can take it inside the spherical average and just write spherical average equal to spherical average of y I1, I2, IL. This is what I meant by modulation, right? Because the Lth level solution is again a spherical average, but it's just a modulated spherical average. You should modulate it by this thing. Okay, I've been saying this thing for a while now. I've been also foreshadowing something about it. So let me tell you what this is. Okay, so what we want to calculate, okay, is the question. What is this polynomial? Y I1, I2 all the way up till IL, Q I1, or let me do it in X. Okay, X I1. This is just some variable, doesn't matter. Okay, if you have a polynomial in X, you have a polynomial in Q, and so on. X I. That's the question. Okay, but that's very easy to see. Remember where these y's came from. Y's came from solving some Laplace equation, and then we restricted it such that you get independent solutions. So you get some symmetric trace-free thing, and that is why. But now, if you act the Laplacian on this, what should I call it? I should probably call it something. No, never mind. Y I1 IL, X I1 IL. Okay, grad squared is just del x squared plus del y squared plus del z squared and so on. This, wait, is this how I want to say it? Just give me a moment. Yeah, I mean, I don't know how to say this, but it should be obvious that this is 0. But I will explain it to you. Just give me a moment. Okay, it's clear actually. We can just take an example. Okay, from that example, you will see why this has to be true. For example, let's do grad squared. So this grad squared will go through this y. Okay, let's just do grad squared on say xi1, xi2, just this much, or xi3. Maybe xi1, xi2 is too trivial. xi2, xi3. Okay, level 3. Okay, So this is equal to what? This is equal to del 1 squared, del x1 squared, del x2 squared, del x3 squared, okay, times xi1, xi2, xi3. Now if I1, I2, I3 are different, are all different, if this was just x, y, z, say, then this will obviously be 0. Okay, so it will be non-zero only if I1 and I2 are the same. Right? Just thinking what is an easy, I remember, just give me a moment, I remember thinking this was very easy to show. Worked it out the other day. Yeah, anyway, guess this is it. Yeah, one thing I should have noted is that this is a homogeneous polynomial. Okay, which reminds me of our second class where we solved the Laplace equation and we wanted the polynomial solutions. Okay, and we showed that the polynomial solutions should be arranged in homogeneous polynomial solutions. So this is a homogeneous polynomial. That itself gives you a clue. Okay, and the second thing, I guess you guys just have to take a few examples. Maybe I'll just leave this to you. Okay, just take a few examples and check that this has to be the case. Okay, for example, I can do a couple if you want. For example, b equal to 2, y I1 I2, I can take to be this matrix 2 minus 2 0 0. Okay, this is trace free and it's symmetric. I can actually put AB here, AA here. It has to be symmetric, so it has to be the same thing. So y I1 I2 xi1 xi2 is just what? It'll just be 2x squared minus 2y squared, so that's just 2x squared minus y squared plus ax 2xy, and that's obviously a solution of Laplace equation. Right? That's clear, right? Because these are just this and that are just the real and imaginary parts of z squared or zeta squared, right? Because remember that in 2D, the solutions of the Laplace equation are just governed by analytic functions, and these are just that polynomial analytic functions. Okay. Okay. Thought I had a more satisfactory way of saying this. Yeah, okay. I know how to say this. Give me a minute. So maybe I can erase this. Notice that, so basically the point is we need to do grad squared on y I1 I2 all the way up till IL on x I1 I2 all the way up till IL, right? So that's just equal to y I1 I2 all the way up till IL on grad squared acting on x I1 I2 all the way up till IL. Okay, but grad squared is just del x squared del y plus del y squared plus del z squared and so on. So let's just do del x 1 on this thing. Okay, what will that give? That will just give delta I1 1, x1, xi2 all the way up till xil. I keep doing Leibniz rule, plus xi1 delta I2 1, xi3 all the way up till xil, plus dot 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 plus xi1 xi2 all the way up till xil minus 1 delta il1. Okay. Now if I do